Hey, Ethan, how are you?
Oh, long time, man. Long time no see. Oh, great. You're staring at my. Great. You can teach me stuff.
Hello, everybody.
Hello.
What are you all doing?
Not too bad. It's Friday.
Yeah,
I just got
here
told
for the
it's a
weekend.
long weekend. I didn't even know it was a long weekend.
Is it a long weekend? So there's no
Yeah,
working Monday?
Veterans Day is Monday is a holiday.
Oh, I wasn't even aware of that.
I
I'm traveling, so I didn't even notice. That's great. So yeah, it's a couple minutes past the hour, so let's get started. I am today. I'm going to speak about parameter efficient fine tuning and quantization for large models. So usually I deal with large language models, but this it's concept generic to any neural network. So it could work with vision models or with diffusion models or whatever. So the idea behind it is that like as the capability of the latest models advances, the size of this as well increase. And say you if we're dealing with an open source LLM, which is usually small, like we're talking about a class of 7 billion to 8 billion parameters, um, uh, you can run it on your computer, but then like usually if you're doing a project that you want to fine tune them, and then that opens a whole new can of worms because there are a lot of logistics, um, because basically you need lots of RAM, and that by lots of RAM I mean probably in the order of 100 of gigabytes of RAM, and then that means that you're looking at using NVIDIA GPUs that cost multiple NVIDIA GPUs that cost about $20,000 a pop. So it really goes out of control, and you need to be working at a big company. So us in our academic environment, we do have lots of GPUs, but they are comparatively smaller. So some private labs have A100s or H100s, one or two maybe. That might or might not be enough. Or if you're using the HPC, you're going to have a like probably access to 10 P100s or B100s that are even smaller. But if we can somehow pull all of those resources and do something with them, we can actually get out with it. And there are a lot of clever tricks around, and two of those, the ones that are the most popular, are uh, first parameter efficient fine tuning, and that's also sometimes commonly known as LoRA. So LoRA is a specific type of parameter efficient fine tuning, but there are others. But I'm going to use them interchangeably today. And what that does is that you instead, when you're training a model, instead of doing back propagation during the optimization step over all of the parameters, you introduce side models that I'm just going to call it connect to the main network. And they're really, really small with respect to the actual size of the model. So that means that you do not have to spend a lot of memory into optimizing that and learning, and it's really fast. And the other technique is quantization. So quantization, the idea behind it is that these giant models are basically tables of parameters, and parameters are nothing but floating point numbers. So the native format in computers to represent this uses 32 bits, and that is um, 4 bytes per number. And if we are looking at an 8 billion parameter model, just multiply that 8 billion by 4, and that's the more or less the amount of RAM that it takes to load that model into the server. So you can instead make a trade-off between the size of those numbers. Instead of loading them as 32 bits, you can load them as 16, 8-bit, or 4-bit. That is a half byte precision, and slash your memory footprint such that you can run these huge language models in consumer-grade GPUs. And by this, I mean you could have a gaming computer in your home. You could load it there and train it and fine-tune it there, or it could be on your laptop, or it could be like even if you have, say, one of those new fancy Apple Silicon MacBook Pros that have 128 gigs of RAM. If you quantize Llama 3 400 billion parameters, you might be able to fit it into that laptop. In contrast, if you were using the native version, you need a rack with servers in a data center. Just load it, not to train it. So these powerful tricks allow us to say access to LLMs in a more egalitarian fashion. Like we can democratize these models to implement our own research agenda. And so what I'm going to do today is that I'm going to base the demo in 2 examples that I found on the internet. And first, I'm going to use the HPC to fine-tune a vision model using LoRA. And then I'm going to use another server that I have access to at the university to load Mixtral 8 by 7 billion parameters, which is about 46 gigs of RAM, into a server and fine-tune it with quantization and LoRA. So we'll see how that size and footprint of the memory changes as we apply these operations. So buckle up. If you have any questions, please interrupt me, and I'll happily try to get to answer them. So let me open. I test this ahead of time, but I don't have this is not scripted, so I will just be sharing my screen and starting the session. We are at the open on demand interface of the HPC. So I'm going to start a new job, a Jupyter job. I want 4 cores. Let's do 1 hour. I just want one GPU. So let's just try 16 gigs. Let's launch it. It'll take probably a minute to get it. But once we get it, yeah, there it is. So while I open this, I want to ask everybody here in the crowd: have you ever used any of these methods on any of your research or work? So it means it's probably not. So hopefully this will be of use. And like if you haven't used it and don't have an immediate need for it right now, you can always refer to the recording, and this will be useful. So I'm going to create a new notebook. I'm going to make the font here larger, and I'm going to start with copying and pasting the snippets and just explaining them here. So first thing, is we need, this is a Jupyter notebook. We have access to 1 GPU, and we need to import our dependencies. So here we're looking at multiple ones. The main one is the transformers, which has the code to run the vision models. We have accelerate, which is a dependency that we need in order to run the Quantization and LoRA. PEFT is the parameter efficient fine-tuning library. It contains the implementation of LoRA, and PIL is just a library, like an image processing library. It's native to Python, so you'll have it if you have an installation. We're going to be working with a model called VIT, which is a vision transformer posted by Google. This is already trained or pre-trained. And then we're going to be looking at a data set called Food 100, Food 101. So we're like, since we just want to showcase what is the effect. We're gonna not actually make predictions. We're just gonna make it run for one training iteration, and as long as it clears, then we're good. So when you're using Hugging Face, you usually use this utility function called dataset to fetch whatever dataset by its name. And then we need to usually to do some pre-processing. We want to see what are the labels. For example, this third label is baklava. Let's see what is the first one, apple pie. Let's see what else do we have, bruschetta, waffles. So, you know, like you can get it. I'm not going to show images, but you probably get the gist of it. We're classifying like this is a picture of something. Tell me what it is. So then the first step is, well, three steps is to load an image processor. So what is an image processor? Usually it takes raw data. It's stored like images could be stored as JPEGs or PNGs, GIFs, or whatever. We need to load them as bitmaps, and we need to do some transformations for them. The image preprocessor handles the operations that the model already assumed that are going to are going to halt when we run the data treat. Because we're also going to add
Enrique,
ours.
there's a question
Yes.
in the chat window.
Yes, sorry, I didn't see it. Yes, so you will get the code repo. So I'm going to save this notebook and I'm going to upload it to the repo. Right now, let me just open it here. GitHub UA AI Makerspace. So I will update it to add session 6 after we finish. And if you scroll down here, you'll see in the table that we have a link to the notes and a link to the recording. So the recordings are always lagging because we have just a limited amount of students who edit them, but eventually they will trickle up. So notes will be soon after we finish, and the video will be probably in 1 or 2 weeks. Be up in 1 or 2 weeks. Nathan, thank you. If you see somebody else asking a question, let me know because I do not see the chat window. Okay, so come back to this. We also want to do some transformations. Like we want to center the image. We want to normalize it by normalizing it. I'm not exactly sure what it means. I suspect that it means the colors have to be shifted to specific hue. We want to make sure that they are on the same direction, they have same size. And then we want to map the images from a bitmap to an actual tensor for the device. So there are a bunch of utilities that are relevant to this example, but not relevant to the concept. So let's just glass for them. So we create this normalization pipeline that uses the image processor that we loaded previously. Then we define these transposes where we do this composition. We make it tensor, then we normalize it. It's probably also normalizing by batch, making it such that the mean is 0 and the variance is 1. of the values of the batch. And then some utility functions that are going to take a batch and apply these transformations. There are two separate ones, one for training and one for the validation dataset. Trying to see, yes, so the only difference between them is that in training, we're randomly flipping horizontally the images. This is just a trick to make it the model more resilient. But during validation, we don't want to do anything like that. We just want to stick to data that we have. So we create these two functions, one for the training preprocessing, one for the validation preprocessing. Then we are going to load those data sets and say, if we look at the train, yes, we see that we have 4,500 images. And in the validation data set, 500 images. So we also need this utility function that is going to give us an idea of what's the effect of LoRA. So as I was mentioning at the beginning of this talk, if you're fine-tuning something which is essentially supervised training, all the parameters in the model are going to be updated anytime that you do a back propagation step in the neural network training phase. With LoRA, we create an adapter that sits besides the parameters, and we just train it. Then some matrix decomposition operations is applied to the different layers of the network that we want to adjust, such that all the contribution from training is captured in that adapter, and we hold the actual parameters frozen, and that allows us to save time. So with this utility function, what we're going to see is what is the total number of parameters. That means the original transformer, and the number of trainable parameters. That means how many elements of the LoRA adapter are going to be trained. And we're going to see what is the proportion of trainable parameters with respect to the total size of the model. As soon as I run this, I think it's going to be pretty clear. And then we need to actually load the model. So if you have used Hugging Face before, you've seen these auto model classes. This is it's just a utility that, like, there are different models to do image classification or text classification, and each have different details, but the overall principles on top of those are the same. So the details are the ones that vary a little bit. With the automodel classes, you don't have to change your code as long as you specify what is the task that you're trying to achieve. And here we're doing image classification. The code is going to handle loading the correct class for that specific model. So the only thing we need to specify is this for image classification, and if it's the automodel class, it'll resolve internally what is the actual concrete class based on the model checkpoint. Now, if I scroll up a little bit, we're using this VIT base patch 16. So VIT stands for Visual Transformer, or Vision Transformer, sorry. And it's similar to, say, like VERT, but for images. It's a gross oversimplification, but you get the idea. So we have here a class called model. Excuse me. So, and we see that, we have multiple layers inside of it, which first we have the embeddings, we have the convolutional layers, some dropouts, attention mechanisms, linear layers, like for the attention, which are the query key value, etc. And I want to run this function here that we defined above to see what are the number of trainable parameters for this model. So we have a total of 85 million parameters, and they are all trainable. That means that we are training 100% of those. But now we are going to apply this LoRA transformation on top of it. So let me find, where do I have that specific? So this is probably the most important part of this demo. We're going to apply the LoRA, we're going to change this model to the LoRA model. So in order to do that, we need to define a configuration. We use the LoRA config and this utility function that transforms our base model into a LoRA model. Now, LoRA stands for lower rank. I don't know what's the A for, but how it works is that, like on a neural network, you have multiple linear layers that you can think of those as matrices. So matrices are giant square arrays or two-dimensional arrays. And they have like a large number of rows and large number of columns. And when you multiply them, you get a lot of parameters. So there are mathematical operations to decompose them, like factorize those matrices into lower rank ones, which means that they are significantly smaller individually. But once you multiply them, you get the original one. And this is the principle here that we introduce a decomposition, and we're just training one of those. Then after we do that, then they are multiplied together to get the equivalent to the original one. And rank is basically you can think about it as the dimensionality of the matrix. So it's much more nuanced than that in linear algebra, but it is a way to think of, like a matrix that has 16 elements in its diagonal. More like if there's a mathematician here, that person is going to be cringing by my description. But that's the way that I sort of understand it. I know that, like some of the components might not be independent of another, and that increases the number of columns without increasing the rank. But it's not really important. We have some hyperparameters. The most important one is what are the modules of the original network that we're targeting. So you see query and value here. If I scroll up a little bit, you're going to see that in the attention mechanism, we have query value, and that these are linear components. So one key observation about this is that LoRA only works on the linear parameters. It doesn't work on the convolution. It doesn't work on the embeddings, as far as I understand. But that doesn't really matter because most of the parameters in the transformer architecture are linear operations, so we can use it a lot more. And we're going to save the classifier model. So once we have this, we need to apply that that composition into the model. So we are going to get this parameter efficient fine-tuning model from model using the configuration to generate the LoRA model. And so what do I get here? So it is complaining something about its bytes, but I am not actually using it. So let me see if I can.
This is an HPC machine. Do you need to have a pseudo on that?
No, you never have pseudo on the HPC.
So the CUDA is nothing to do with HPC. I thought it couldn't access the GPU.
Oh, yes, I can access the GPU. But bits and bytes is causing trouble because we have an old GPU. Okay, so I'm gonna kill this and okay. Need to restart the kernel. And I'm going to need to run all this again. So when you do the quantization, I found out that I could make it work on this specific GPU. So that's why I'm going to show it in another computer after we finish with this notebook. I suspect that when I installed the bits and bytes package, I got some interaction that wasn't expected. So let's hope that, yes, it works now. So when I uninstalled bits and bytes, this worked. So now let's see what is the size of parameters. So 86 million parameters. Let me select this. Here there were 85 million parameters, roughly 86. And we have 86 and a half. You can see that this one has more parameters. The reason for that is that the LoRA model has those new adapters attached to it. But the amount of parameters that are trainable are only 667 and that means that we're only training about 0.77% of these parameters. So that will translate into smaller memory footprint and into quicker training time. Now you may think about like, why is it taking less memory to train it if the LoRA model has more parameters? Because even though some of those parameters are frozen, they are still in the GPU. Thing is that when you deal with these models, you have two modes. You have the training mode and the inference mode. And the inference mode is straightforward. You just load it and run it. But when you're training it, you're using an operation, an algorithm called backpropagation, which is a type of numerical optimization. And this backpropagation relies on the notion of gradient. So a gradient is a value that is associated to each of the parameters. That means that if we're training this model that has 86 million parameters, when you consider the gradient, you have another 86 million elements of the gradient. So you duplicate the size. Then you use an optimization algorithm that contains like the main one used is called Atom, and it has a concept called momentum. And that momentum is computed using 2 copies of the model. So you triplicate the amount of storage in addition to the actual base model that you have. So you need to keep 4 times the amount of memory, in order to train it in training mode. Now, when we are using LoRA and we reduce that to 0.77%, this 0.77% is the thing that is multiplied by 4 when we're training. So in the end, yes, you end up using less memory. And it is basically faster because you need to work through less number of parameters. So we're almost there for this notebook. We need to define the training arguments. So this is just basic, like, like, how do you want to call it? Like, it's the fine-tuned LoRA PUD 101 version. We want to evaluate an epoch. We want to set a learning rate, a batch size of 128. We are loading using 16 bits, 14.16 bit. We don't want to push it to the hub. And then we want to, in addition to the configuration, we want to evaluate it. So how are we going to evaluate it? We're just going to use accuracy. The accuracy is just what's the proportion of correct answers that you get from the predictions. We need a calculator function, which is just one additional utility used to select the data out of the relevant data structures. And we're just going to instantiate the trainer. Now here, we need to say what LoRA model, because we had the base model and the LoRA model. So we're going to train over it. We define the arguments. We define the training validation data set. We had this image processor, compute metrics, and collect function. So let's hope that we can see that progress bar. And we don't. Obviously, we don't. Pixel values. Yeah, I'm not sure why you don't get it. So let me try something else here. Probably missing a dependency. Okay. Of course, the classic, it worked on my computer, right? Okay, so for the sake of time, let me jump to the other notebook that I ran to completion. Just a sec, and I'll just show the result, and then we can move on to the Mixtral example. So was assuming that, like we worked through the bug that we showed, we're going to get this, and you see that we start with this training loss and it's reduced in each epoch. Additionally, like I had, like first I ran a training without LoRA, and we start with a significantly higher training loss because this was not fine-tuned. And you see how the validation loss started decreasing. So it went from 0.6 to 0.17, and then it went to 0.11, 0.10. Then we can see how then there was some diminishing returns. Like at this point, we stopped at the 5th epoch. We stopped the decrease in the validation loss, and then we started actually increasing the validation loss. This is a sign of overfitting because the training loss still went down, but the validation loss started to wobble around that value. It's not relevant for today's session. The important part is that you know how you can do the LoRA adapter on a model. So just want to take a bit and ask if so far you have any questions. And if not, then I am going to switch to another console. Okay. So here, this is a server where I have a slightly access to. It's not mine. So please don't tell that I'm using it. But I've had access to other more modern GPUs, like H100 is one of the top of the line GPUs that you can get today. And one of the nice advantages of it is that you have 81 gigs of RAM each. So what I want to do is that I want to apply same principle, but add the quantization mechanism here. So this time, instead of a notebook, I'm going to use IPython, which is really similar. Actually, before doing this, I'm going to use tmux. And just to verify that I'm on the same computer still. Yeah, we still see the GPUs, IPython. Okay, so let me identify the notebook that the example that I was looking at. Hold on just a sec. Okay. So we are going to look at the model. So let me share another screen. I want to show you. So this is the Hugging Face Hub, and we're looking at Mistral's. Mistral's dataset. So we're going to look at this, the Mistral 8. We're going to call it path. So this NeMo base has 12 billion parameters. And if we look at the files, you can see that there are 5 shards that are about 5 gig each. So we're looking at 20, about 20 gigs of RAM, probably 20, like 19 or something of raw data. That means that you have to have a lot of GPU RAM here. Like if you have, say, a 4090, it might be not enough. But if you have one of the data center GPUs, yes, it's absolutely going to be enough to load it for inference, but absolutely not for training, because you need to have those 4 copies. So let's see if we can squish it out by using quantization and by using LoRA. So I'm going to go back to the console. And I'm going to start loading it. So first, I want to load the model. Let me do some imports here. And let's use the same auto class utilities. Ethan, can you see large enough the font size here?
Just make it a little bigger.
Okay. So you can even see how like loading this model takes 10 seconds just by the sheer size. And I want to see like how do we know what's the size of the model on RAM? So let me find a function. Just a sec. So I found this. Oh, yes. Sorry about that. I was missing this snippet. So this Mistral Nemo is 46 gigs of RAM, or almost 47, which is about the size that we got in our back of the envelope calculation. Let's just make this a function. Okay, model, size, model. So 16 gigs. But let's do the quantization trick. So this is the other key insight of today's session, is that we can load it in 4 bytes. And I'm just going to explain what does that mean. So if you use, like you don't have to do this algorithm for yourself. You're going to use a utility called bits and bytes, which is just the name of a package that they already like have this code that loads the values and maps them to their lower precision counterparts. There are many ways to do quantization. Like you can just reduce the precision, or you can even change the data type. Like you can map a floating point number to an integer, like an 8-bit integer or a 4-bit int. You're going to sacrifice performance, but it still works. So there's like you need to figure out what is the amount of performance that you're willing to let go to save enough footprint in your machine. So it doesn't necessarily run faster, but it allows you to do stuff that you couldn't do before because there was not enough memory in your system. So in here, we're loading in 4-bit. So you need just to pass an extra parameter called quantization config. And there is an object that contains those parameters. We are specifying that we want to use 4-bit. We want to specify the data type that backs this quantization, which is bfloat16. And what that means is that we are cramming together 4-bit parameters into a single float 16-bit data variable, or like item in the memory. So it'll do bits and bytes will do this unpacking for you, packing and unpacking for you. And this is the quantization algorithm that you want to use. NF4. I'm not acquainted with the details, but it's some sort of like numerical wizardry that if you read the paper, it might make sense, but you need to be aware of the fine-grained details in order to be able to leverage it. And that's exactly what I do. So once we loaded this, let's see what is the model size. So now it's 7.7 gigabytes of VRAM. So let's see what was the reduction we got. So now this quantized version has about 17% of the memory footprint that we had in the beginning. And I mean, that is great. Like, as long as it works, then that's pretty awesome. But what do we have to like? Still, we can merge together these techniques like the quantization and the LoRa fine tuning to squeeze even out more of the hardware that we have available. So that's exactly what we're gonna do. So for that, I'm just going to copy and paste the snippets that I have here ready to move forward with that. So when we're dealing with text, similarly to the image processor that we had in the vision transformer, we need a tokenizer. The tokenizer takes a string and splits it into more or less words that those are the tokens. And we need to add certain specific special tokens that indicate what is the end of the sequence, of what is the start or the end. Like, you know, these LMs behave as chatbots. So who's the actual user, who's the assistant? These tokens take care of that. We need also to this quantization. It's meant to be for inference mode. So if you want to actually train it, quantize, we need to prepare it for it. I think that this is just some configuration in the model. But if we see the model, you see that this is the Mistral that is already linear in 4-bit. So like, if you get back to this recording and try to see its layers, you'll see that this is like more or less standard transform architecture, that you have an embedding, and then you have a decoder that has attentions, and each attention has multiple linear layers. These are going to be the targets of our LoRa PEFT, and then it has this linear classifier. But since this is already quantized, it has 4 bits and it's prepared for training. So now we want to do this LoRa quantization. We need to specify a configuration for that as well. For the vision transformer, we were saying the rank to 16. This time it's just set to 64. That means that we're going to have more parameters to train. Just like it's enough. It's like we can still do that threshold. And then we want to get the model with LoRa layers. So let's see what is the shape of this. So like, you can see that now it's significantly longer because it has all those adapters in there. And you see, you can actually, the embeddings do have LoRa as well. But we have these linear 4-bit that have a LoRa dropout, and then some LoRa adapters. So that is interesting in the sense that, let's see, what is the model size? So now it's 16 gigabytes. So if you notice, we went from 42 or 46 gigs RAM down to 7.7, and now we're up to 16 gigs. So in a sense that we're probably letting go a little bit of a significant amount of memory by accommodating this LoRa adapter, but it might work well in terms of performance. So this combination is sometimes called Q-LoRa, and that stands for quantized LoRa. And it's something that you'll see, like, if you read papers that come out on EMLP, ACL, you'll see this all the time. I forgot that we need a data set to fine tune on. So this is an open system data set. It is like a conversation data set. So if we see what is the like how does the data look here? This is a message in Italian, so I'm not sure that I understand it. But let's see if we can find one that is. This is Japanese. Okay, I understand this is Spanish. What's the best way to cook a chicken? So you can see that these are the special tokens. Like this specifies that this is a user message. Like if someone actually asks this to an LLM, and then this signals the start of the response of the LLM. That's why it's marked as assistant. It says more or less the best way to cook a chicken depends on the personal tastes or preference in flavor. But some of those methods are popular include grilling, baking, sauteed, or fried. Then like it doesn't matter the rest. So this is what we're looking at. We need actually to apply some pre-processing as well. And if we see the dataset tokenized, train, you'll see now we have like long lists of numbers. These numbers are the token IDs. It maps, like the tokenizer maps a string to the identifier of each word. That this is what you see here. It's not meant for human consumption, but it is how we indicate the words to each transformer. We need a little bit more pre-processing stuff, this data collator, which is going to help taking care of batching. And then configure the trainer. So we're specifying what's the batch size. We're setting a batch size of 1. Let's see if, well, no, gradient accumulation steps. So this is purely stochastic gradient descent that we're updating for each instance. I do not recommend this, but it doesn't matter for the sake of this demonstration. 5 epochs. Then we're just specifying all this here. We're using Atom 32-bit. So finally, we're going to run the training. Now I hope that it doesn't crash on me. Okay. All right. So what you're seeing here is each time that the transformer has one input, it updates and calculates loss. So this is an point-wise loss. And you see that it like bounces around because it's purely stochastic. Like usually what you do is that you do batch stochastic gradient descent, in which you pass either several dozen examples and accumulate them and then compute that average loss, or just pass a significantly larger batch that will help with numerical stability. But in the end, like the trend, like if we were plotting these values, we would expect it to see it to bounce around, but decrease that value. And I want to show you what is the CPU or GPU usage. So what we see here is that we have 2 GPUs, and those 2 are being used for this process, and they are being utilized asymmetrically. But let's see, if we'll take a look at the memory, one of those is using 32 gigs of RAM, and the other is using 19. So this is around 51 gigs of RAM. And let me just take out my calculator. So I want to see what's the number of times the size of the model that we are using on the GPU. So 18, 9, 0, 0 plus divided by 16,600. So like I'm gonna put this here. So it's about 3 times, which accounts for the actual model that we're training with LoRA adapter and quantized, the gradient and the momentum. So this one only has one single copy of the parameters for the momentum. So if you recall, when we started this and loaded the model without quantization, it was about 14.6 gigs of RAM. If we had to do it without doing quantization and LoRA, that would have been about 130 gigs of RAM. So we actually did reduce a lot. And yes, these GPUs are on the same node. This is a single node multi-GPU setup, and I didn't actually explicitly configure it to use both. Instead, Hugging Face figures out how to distribute it, so we could have finer grain control if we want. Or you can make it a multi-node setup if you're using something like DeepSpeed. But yes, so that's it. That's the end of the demo. And yeah, hopefully I'm gonna just kill this, and we'll see down how the use of the memory once I exit IPython frees up. So in the end, what we achieved was to load a big LLM of 12 billion parameters. We saw that it took about 14.6 gigs of RAM. Then we applied quantization, and then we applied LoRA such that we could do a faster training with less parameters. And we saw that we were able to, even though we're using 2 GPUs for training in this example, we could have explicitly pinned it to a single GPU. And having 30 gigs of RAM, it's enough to fit in a single one of these GPUs. But if you were using the HPC and you were using one of the D100s that has 32 gigs, maybe you want to split it in two GPUs. So that could still work. So you need to get creative with your configurations, but you're actually able to pull it out. So that is it for today. Do you have any extra questions? Okay. Goodbye, Jonathan.
Thank you.